Cool. So the meeting is now being recorded. So yeah, you guys can watch it back afterwards, and I've let the guys know who said they're not going to be here that I will record it, and they can hopefully log into Teams and see it. If anyone has any issues not being able to see it, let me know. I will download the video from my OneCloud so that we can I can upload it to YouTube for other people to watch. Cool. So yeah, it's the last proper night class of the year because next week you guys have your end of term exam. It will only be about the topics that we've covered this term, as far as I've seen reading through the exam. So it's just going to be on cables and diagrams, circuit diagrams, location drawings, that kind of thing. Just the basics. But cool, let's get started tonight. Cool, we'll just do a little bit of revision. Cool, so what are the key factors to consider when choosing a cable installation method? So what are some factors to consider when choosing a cable installation method? Cost, yeah. Environment, yeah. The load, that's a good one. Yeah, accessibility. Yeah, size of the cable is always a good one to think about. Distance, yeah, the distance you have to cover. Cool, I think those are some pretty good answers. Cool, so environmental conditions, yeah. So moisture, temperature, is it going to be put through any mechanical stresses? Mechanical protection, do we need to cover the cable with trunking? Do we need to put a guardrail over it? Compliance with AS NZS 3000, always. Accessibility for maintenance, yeah, it's always a good one. Aesthetic considerations and space limitations. So there is that. So, for example, if we're running cable, we don't want it to always be kind of out in the open where people can see it's ugly. Yeah, I had one client ask me, "Oh, how much would it cost to run the cable underground so I don't see this overhead wire anymore?" Yep, that's a good one, Stefan. And sealing, yeah, that's something that we haven't put on here, but yeah, especially if you've got to fire seal it. But yeah, the client asked me about the underground, and when she saw the cost, she almost about fainted. She thought it was going to be a quick, simple, easy job. Didn't realize the costs involved. But what challenges might arise in high vibration environments? The areas where there's a lot of like vibrating machinery or there's high wind gusts vibrate the building. Yeah. Damaged cable, yeah. Yeah, definitely. Yeah, that's a good one. High vibration could loosen the support systems. Okay, so connections and terminations may loosen over time due to vibration. Um, another thing you guys should know about is that copper actually heats and then cools down and contracts over time. So when we do up our circuit breakers as tight as we possibly can, even though we've tightened them extremely well, over time they can still heat up, cool down, and the copper eventually changes shape to suit the circuit breaker. So manufacturers' recommendations or requirements that we're supposed to follow is that they're torqued down to a certain specification every 6 months, which obviously for residential isn't practical, but in commercial environments, a lot of guys who do maintenance for commercial buildings have it in their contract that every 6 months they come through and torque down all of the circuit breaker connections. Yeah, mechanical damage to the cable or insulation. Increased wear and tear on the installation, requiring extra securing methods like flexible conductors or vibration-resistant clamps. All good, Blake. We've been recording since the start, and we've just been revising, so you'll be able to watch the start of it later on. Cool. What installation methods would you recommend for running cables in an area where the ground is hard rock and cannot be dug into or chased? All good, Jack. We've been recording the whole thing, so just don't watch the beginning later on. Overhead lines, yep. Conduit, overhead or catenary. Yes, some of the recommendations: aerial conductors or cable on cat wires, surface mounted conduits or trunking. You can use steel conduit if it's low to the ground. Using mechanical protection to avoid damage when the cable is exposed. Yep. Another thing, like we looked at last week, you can have the cable at a certain depth, and then you could backfill. So you could increase the ground level if you really needed to. So you can put your cable down, bury it with so much sand, cover it with more topsoil, and then concrete over the top, and it wouldn't be that much of a height change. It's not always feasible to do that, so it's not listed as one of the options. Cool. So tonight we're looking at secure connections, cable jointing, and AS/NZS 3008 1.2, which is all to do with Unit Standard 32613. One thing to note, for AS/NZS 3008, there's two versions, 0.1 and 0.1.2. So 1.1 is for Australia and 1.2 is for New Zealand. Even though they're joint standards, 1.2 is the temperatures for New Zealand when we are talking about average temperature above ground and below ground. So if you have to look at cables to suit later on in your apprenticeship, you need to use 0.1, 0.2, because if you use 0.1, 0.1, you'll be using the Australian standards and you'll overrate your cable, which could be costly in terms of overspending on cable. Cool. So there are three main methods of connection. Cool. So flexible cord using approved plug and sockets. So this is the most common method of portable appliances. It provides flexibility, allowing the equipment to be moved and disconnected easily. Key considerations: ensure that the plug and socket are approved for use in New Zealand and suitable for the environment, e.g. IP ratings for outdoor use. So that's just making sure that if it's an outdoor appliance, we're using an outdoor rated plug and socket. For example, caravan leads have the nice blue plug-in sockets. You can get IP rated sockets and plugs that you plug in, you screw it tight. So that way it's a nice sealed connection. So we shouldn't just use, this also goes for obviously, power points. You want to make sure you get the outdoor rated power points. Can anyone tell me a couple features of outdoor power points other than them being completely sealed that make them ideal for being outside? Yeah, I was hoping someone would say that, Sasha. Yeah, so if the UV rated as well. So if you look at a lot of the outdoor power points, they all face down, so the connection is down, so it's harder for moisture to wick up into the power points. Okay, guys, I won't wait for everyone to get the notes down because we do have this as a recording. So you guys can watch it again afterwards and take notes. So I highly recommend you do that. It's up to you how many notes you want to take. That's fine. If Connor comes late, yeah, he'll let us know and then he can watch the recording back. Yeah, so it's great that I can finally know how to do this. Cool. So flexible cord or flexible cable from a permanent connection unit. So this method is used for appliances or equipment that are semi-permanent or not meant to be moved often, like fixed appliances. So your air conditioning units, your hot water systems, towel rails, heaters that are wall mounted, in rental properties more than everyday homes. You'll find a lot of Housing New Zealand state houses, when they put heaters in bedrooms or living rooms, they'll permanently wire them in because they've got a history of tenants taking them when they go. So key considerations: permanent connection units must be accessible for maintenance and comply with relevant standards for safety and durability. So don't stick it behind the hot water cylinder. Don't stick it in a cupboard where no one can reach it. So it has to be accessible for maintenance. You can't put it behind the heating unit or behind the aircon unit. So many times I've gone to jobs and the isolator for the heat pump is behind the heat pump. And some guys have also mounted an isolator to the heat pump itself, thus voiding the warranty and making it just, yeah, bad practice. Cool. Flexible cord or flexible cable using suitable connectors housed in an approved enclosed switch or terminal unit. So this method is typically used for fixed installations where the cable needs to be connected within an enclosure for protection, e.g. light fittings or ceiling fans. The key considerations: the enclosure should protect the connection from environmental factors like moisture, dust, or physical damage, and must comply with AS/NZS 3000 requirements for connection integrity. So yeah, this is all about like your light fittings and your fans. So it's got a probe switch or terminal unit. So just random facts, not a lot of you guys will know. Those pull cords that you sometimes see in older homes for the lights, they don't manufacture or sell those anymore in New Zealand. They use them a lot in the UK, but they're not compliant as far as I know here. You just can't get them because I've gone to replace them and the wholesalers said, no, we don't stock them, they're illegal. Although that may just be the wholesaler not wanting to stock them anymore. Cool. Some real world scenarios. Cool. Hairdryer in a gym changing room. You've been asked to inspect the installation of a hairdryer in a busy gym changing room. The room is often damp from steam with high foot traffic. The hairdryer needs to be securely installed to prevent theft, and the connection must be able to withstand moisture and constant use. Cool. So what would your recommendation be for this install? Just one thing. So, Ryan, your answer for the RCD, because it's a commercial space, it doesn't need to be on an RCD. However, you could argue the fact that it's in a damp situation means it needs one. It would depend on how close it is to the shower or hand basin. So they're not giving us enough information. My preference is always to put things on RCDs, but in a commercial space, you don't always have to. Cool. So recommendation. In this environment, the best solution should be a permanent connection unit with an appropriate IP rating, at least IP44 or higher, to protect against moisture. The hairdryer should be mounted securely to prevent theft or tampering. So when you go to look at hand dryers in the mall or in public bathrooms and that, the hand dryers are always pretty solid and you usually can't see where the screws are. Once you put that cover on, you can't see them anymore. Cool. Scenario 2. You are installing a motor outside a warehouse to operate a large ventilation system. The motor will be exposed to rain, dust, and potential vibration during operation. Additionally, the motor's controls will be housed in an enclosure nearby. The challenge is to ensure that the connections are protected from weather and that the installation complies with safety regulations, particularly with regard to moisture ingress and secure terminations. What is your recommendation? Anyone else got any recommendations for this job? Silicon, flex conduit, stainless steel screws, yeah. Cool. So the recommendation for this one is for this outdoor motor installation, you should use an IP-rated enclosure for the motor's electrical connections, ideally IP65 or higher to protect against dust and water. The motor control should be housed in a similarly rated enclosure with glands used to ensure that no moisture can enter at the cable entry points. To address potential vibration, use vibration-resistant terminations, e.g. crimped or bolted connections that won't come loose over time. So there's a lot to think about there. You guys got most of it apart from the specific IP rating. So you can find tables online that list what the IP numbers mean. And also cable glands are always good for the point of entry because most likely you'll be using flexible cable for this instead of the other option is running conduit everywhere. And sometimes flexible cable is just a lot easier and a lot better with vibration. And yeah, so the terminations, crimps or bolted connections, so they won't come loose over time. Cool. Scenario 3, portable appliance or a drill. You are tasked with setting up a portable drill for use in a construction site. The drill is frequently moved around, plugged into different socket outlets, and used in various positions. What is your recommendation for how to install this and how to get it to work? Yeah, flex cable. Yeah, test and tag. Every 6 months, test and tag. Right. It's a portable drill, so I would say it's either like a mag drill or a drill press or for drilling bigger holes, not like your normal portable drill. Doesn't say whether it's single phase or three phase, it just says it's a portable drill. Yeah. Cool. So recommendations for this one. For this temporary connection, a flexible cord and plug should be used. It should be appropriately rated for mechanical wear and tear, such as rubber insulated cable and plug top, which is durable and designed for heavy duty environments. I think a steel wire armor cable wouldn't be either a battery drill. Sometimes you can't get a battery drill big enough to do some jobs, especially if you're went on the bigger side of the SDS Max. Some of the bigger, my SDS only goes up to 22, 25 mil. And then if I need to drill like a 40 mil hole through concrete, I need to use a quarter drill. I don't know if anyone else has got a battery one that'll do that. Yeah, so steel wire armor cable for this. Yeah, that's fair. That's fair. But yeah, just for any labor on a job site, steel wire armor cable, they'll probably just whinge and whine. So heavy duty flex, like triple layer insulation, would be good. Yeah. Cool. Just a way of doing attendance, just throwing a question out there. Now that we're getting towards the end of the year, what's everyone's plan for Christmas? Are you going away, spending time with family, jetting off overseas, camping? Yeah. Yes, Cody. Oh fuck, sucks, bro. Being on call. Oh, you guys are working through. Do you get a break afterwards if you work through it? I don't know about the beach. Water skiing. Nope. Yeah. Hunting and fishing with the fam. Swim. Yeah. 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 I know some guys who are working through. Yeah, fair. I selected all my Christmas shopping crap. Yeah, no, some of the guys who are working through. Yeah, that always sucks. Some of the guys I know are working through there. They've agreed to work through, but they get a holiday in February to make up for it. But yeah, I guess not everyone gets that luxury. Cool. So, introduction to cable jointing. Now, I know cable jointing is its own kind of, I guess, trade in itself. I have met and worked with a couple cable jointers out in the field. Watching them do it live, I told myself as soon as I saw them do that, I would never fucking touch it. But that's just me. I know there's a lot of money in it, but no, thank you. Cool. So in electrical work, joining cables securely and safely is essential for both functionality and durability. Different environments and applications require specific jointing methods to ensure the connections withstand factors like moisture, vibration, and heavy loads. Cable jointing involves two main steps. One, connecting the conductors. This is the physical joining of the cable cores, the conductive parts of the cables, which can be temporary or permanent, depending on the connection method. And insulating and protecting the joint. Once the conductors are connected, they often require insulation to protect against environmental elements, prevent short circuits, and ensure safety. So we're talking about permanent connections, like your crimps. Then you're using things like heat shrink, Raychem, or like amalgamating tape. And if we're talking temporary, sometimes we're doing IP-rated J-box with cable glands, or if it's inside a sealed junction box, preferably with a bit of tape and at least one or two cable ties to stop it coming loose and pulling out. Cool. Choosing the right methods for each step is crucial. For example, while a temporary connection might be suitable for indoor low-risk settings, outdoor installations typically require permanent connections and additional protection, protective insulation to withstand the elements. In this section, we'll explore a variety of connection methods and installation techniques, understanding when and why each is used. By the end, you'll be able to make informed decisions on the best jointing approach based on the installation environment and the longevity needed for the connection. So you've got to comply. There's compliance with regulations, but then also depending on your job and setting, they'll have different requirements. Like I know on some jobs they do not want you to use J boxes. It's all permanent connection, heat shrink, or if you're doing a plug and socket for a light, that's the only time they'll allow it. Some sites are pretty pedantic about that kind of stuff. Or some will even say, no, you can't do a join, run a new cable, which is really annoying when the builder screws through your cable and it's a 50-meter run. Cool. Conductor connection methods. These are the methods used to physically connect the conductors. They can either be undone or a permanent. So undoable connections. So you've got terminal blocks or connectors, screws or clamps hold the conductors, allowing for easy disconnection. Twist on wire connectors, barrettes, wire nuts. The conductors are twisted together within a connector, which can be removed if needed. Quick disconnects or Wago terminals. These type of joiners allow for quick undoable connections by inserting a single conductor per terminal and clipping down the connector's toggle, which then connects it to the other terminal within the block. Cool. So has anyone heard of barrettes or even used them before? Yeah, so they are an American thing. Cool. And that's what they look like. Yeah, so these are Marex. Yeah, you generally won't get them here in New Zealand just because we don't deem them pretty much legal. I don't think they meet requirements. The only time I've used them is in extra low voltage, so 24-volt control, and they were kind of resin filled. So you screwed them on. As you screwed them on, they tightened and leaked the resin out over the conductors. So I've only ever had to use them once. Cool. Yeah, just one of the many things that we. That's okay, Fergus. I'll mark you down as present and just watch the video later on. Yeah, sucks being on call. Yeah, Wagos. Does anyone's company use Wagos regularly? Yeah, I do like them. They are expensive. They are a little bit pricey, but they are good. So you can get Wagos, like there's the actual brand. Fair enough. I know guys who are like that. But what I will say is a chocolate block connector will melt before a Wago will. They've done tests on it, and the Wago will withstand well over the voltage that they're rated for. But each to their own. For me, they're a little bit expensive for day-to-day use. Yeah, Bizline do make them. They're a little bit less in the quality, but Bizline. Yep. Voltex has a range of them too. Temu Wago. Oh, I don't know. Yeah. Oh, you mean the Bizline ones? Yeah. Yeah, I'm going to have to remember that. That's a good one. Oh, yeah. They're good if you need to undo the connection quickly. Mostly I've used them for, what do you call it? Extra low voltage for daily lighting control. because you can just, it's extra low voltage and you don't need to put them in any form of junction box because it's 24-volt tops. Cool. And then we've got your permanent connections. So soldering, so you melt solder, melting solder permanently bonds the wires together. Crimping without quick disconnects. Crimp terminals without quick disconnect options create a permanent bond. And shear bolt connectors. So once torque is applied and the bolts shear off, the connection is permanent. So they're the ones you crank, and then as soon as it breaks, the bolts, it doesn't have a head anymore, or it doesn't have a place to put your Allen key, so it's now permanent. These are permanent connections. I don't know about everyone else, but the most soldering I've done is for LED strips and computer components. Anyone else done a lot of soldering? Yeah. Electronic boards, yeah. Yeah, LED strip lights becoming way more common in high-end homes. Alarms? Oh, yeah. Some countries overseas, it's a requirement when you do connection twist wires together that you coat them in solder. So people carry around a bottle of solder they'll heat with a blowtorch and then dip the copper conductors in it, and then cover them in insulation tape. And that's what they do for a permanent connection, which works for some Eastern European countries, I guess, but not here. Cool. So insulation and protection methods. So after the conductors are joined, they may need additional protection depending on the environment. Here's how some joints can be insulated. Cool. So you've got your standard heat shrink tubing. So it's applied over a joint and shrunk with heat. This provides a durable long-term protective layer, but must be cut to remove. It is available in multiple colors and should be matched to the conductor being joined. In the case of any earthing conductors, it must be green, yellow, or green-yellow. Okay, emphasis on the color should be matched to the conductor being joined. Doesn't have to be. If you're really desperate and you're joining three-phase cable and all you've got is black, that's fine. But you must use green, yellow, or green-yellow on the earthing conductor, because that's a requirement that the earthing conductor must be green, yellow, or green and yellow along the entire length of the conductor. That's just a requirement for earthing conductors, like we talked about the other week. So yeah, example of heat shrinking. I'm sure most of you guys have seen it on job sites or in the wholesaler. They usually come in all kinds of pretty colors. The ones at the wholesaler are limited to phase colors, but you can get pink, purple, orange, all kinds. I've even seen some that had sparkles. I don't know why, but it did. Cool. You got resin-filled joints. Cool. So encasing the joint in resin creates a watertight protective seal, ideal for outdoor or buried applications. The resin must be broken to access the joint. Heat shrink is also available in a resin-filled variant referred to commonly as Raychem, much like plasterboard is called Jib. And there's kind of an example of some Raychem. Some of it comes like kind of as a flat piece that you bring around the cable, and then you can put a metal former down one side like a zip, heat it up, and it shrinks to a connection point. Just because obviously some joints, once you've made them, they're so big, or crap, I've made the joint, so I can fold that around it, zip it shut, shrink it down. Has anyone done any of the torpedo resin-filled joints for mains cables and things like that, or any other type of resin-filled joint other than Raychem? Yeah, resins off mains. Driveway lights. Oh yeah. And like I talked a bit about before, so you can get self-amalgamating tape or just amalgamating tape. This silicone-based tape fuses to itself, creating a semi-permanent seal that's moisture-resistant but requires cutting to remove. Most common uses are for overhead line taps and locations where a naked flame is dangerous. And that's an example there, the Scotch brand stuff. So yeah, when you get line taps, not necessarily on the pole, but the ones. Have anyone seen the old school overhead mains where it's two separate single wires rather than a neutral screen cable? There'll be the cable will end, and then there'll be a line tap on that, and then a piece will go into the house, not into a mains entry box, but literally just through some steel conduit. So yeah, the line tap will then usually be coated in self-amalgamating tape. Or if you need to do a join on, for example, your neutral breaks in the mains entry box and the cable's not long enough to just to re-terminate it, you can replace the mains entry box and put a small tail of neutral and then line tap that to the existing cable and then wrap it in self-amalgamating tape rather than using heat shrink. Just because the the line tap is just so big that if you were to put heat shrink around it, it wouldn't shrink around the cable. Cool. So now we're going to talk about the sequence for joining a three-phase neutral screen cable. So this is the process. It's a fairly lengthy explanation, but then afterwards we'll watch a couple of videos. Cool. So preparation. So you're going to identify the connection requirements, confirm the jointing method and installation requirements based on the installation environment, e.g. outdoor or underground. You're going to gather the tool and materials, ensure you have the appropriate tools. So stripping tools, crimpers, shear bolt connectors, and installation materials, heat shrink, resin. And then you're going to do safety precautions, verify that the power is off. Verify the power is off always. Wear PPE. Maybe you have to wear the bomb suit if you can't turn the power off. And confirm cable ends are de-energized. Hopefully it's possible. You're going to strip the cable insulation. The outer sheath, carefully strip back the outer sheath without damaging the screen or conductor insulation. Expose the screen, often a layer of braided or foil shield, and carefully fold it back, ensuring there's enough length to reconnect the screen at the joint. Conductor insulation, strip the insulation from each phase conductor and the neutral, taking care not to nick or damage the copper or aluminium conductors. So you're going to connect the conductors, phase and neutral conductors, use a secure jointing method such as crimping or shear bolt connectors. Ensure each conductor is joined tightly with minimal resistance. Screen, you're going to rejoin the screen layers by crimping or bonding the screen wires together to maintain grounding continuity across the join. You can also put metal clips at each end and run a connecting strip of copper between the two. Align all conductors to prevent overlapping, which could affect insulation and fitting of the outer joint casing. Also, another thing to keep in mind, when you're doing a join in a multi-core cable, what you're going to want to do. Yeah, come on. Cool. So you're going to have your cable here. This is where you've stripped it, and say this is your protective outer sheathing here. Cool. You're going to make sure your multi-core cable, you're going to go, that's your red. You can't really see it there, but that's your white. I'll make it green. I know we're not supposed to use green for anything else. Okay, green. Actually, hold up. I can use yellow. Remember, yellow has been superseded by white. There you got your red, your white, blue, then the neutral, then earth. So what I've done here is I've staggered my joints. This is for, and then you have your crimp, 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 crimp. So I've staggered them for the ease of putting the heat shrink on the cable later, as well as there's a gap here. There's a good cut. Yeah, so there's a gap here, there's a gap here, small gap here, small gap here. That way there's less of a chance of them touching and shorting out on each other. It's just to decrease the risk of a short later on and increase your insulation resistance as well. A lot of times you'll get a low IR reading between two conductors if you didn't properly stagger the joint. So yeah, then you're going to insulate the conductors. All good, Connor. We've been recording it, so you'll be able to watch it back later. Just listen in as we go through. Yeah, you're going to insulate your conductors. So individual insulation, apply heat shrink tubing or self-amalgamating tape around each conductor joint to provide individual insulation. Really, this should have been done before you did your crimping. So you slide the relevant heat shrink over each conductor to make sure that you've got some on each. Too many times I've seen guys go crimp, crimp, crimp. Ah, fuck, because they forgot to put the heat shrink on before they crimped it. Guilty of doing that myself. Short moisture protection for outdoor underground joints. Use additional waterproofing such as dual wall heat shrink, Raychem, or self-fusing tape. Encapsulating the entire joint. So apply outer insulation, slide a larger heat shrink or joint casing over the entire joint area. The resin-filled encapsulation, if required. Place the joint in a mold, then pour resin to create a solid weatherproof seal around the entire connection. These days, you just buy the torpedo kit and the whole kit goes around and you leave the kit in the ground. Secure the joint, allow the resin to cure fully, then remove the mold if applicable. Inspect to ensure all components are securely in place. A lot of guys won't wait for the resin to cure. They'll just pop the cap on. Cool. Maybe put some tape around it, chuck it in the ground, done. Cool. And then you do your final inspection. So your quality check, inspect the joint for any gaps in insulation, loose connections, or exposed conductors. Electrical testing, if required, conduct insulation resistance tests and continuity checks to ensure the integrity and safety of the joint. To label and document, mark the joint according to site standards and document the work for future maintenance reference. So if you're doing a joint and a big cable like that, you need to be aware of it and you need to document it. Even if it's accessible, it still needs to be noted that there's a joint there, especially for your records and for the client's records if they're keeping them. Yeah, we had to do quite a few joins inside the main switchboard room at Wakefield Hospital, and so we had to note down each cable of submains that we joined for later records, even though all of them were done inside and above the main switchboard. Cool. So I got a couple videos to watch on cable jointing. Cool. So we'll start with this one. Computer loves doing this to me.
Range connectivity.
Okay. Okay, hopefully that fixes the problem now.
Thank you from TE Connectivity. Cut the resin shell according to the outer diameter of the cable. The cable according to the dimensions given in the instruction. Ensure the cable sheet remains inside the dimensions of the resin shell. Thoroughly abrade the outer sheet for a distance of 50 millimeters. Thoroughly clean and degrease the cable sheet with the solvent wipe provided. Fit the screw connectors using the Allen key provided, or for shear bolt connectors, tighten the bolts until they shear. Really clean and degrease all surfaces of the joint. Insert the core separators between each core. Position the resin shell centrally over the connector area, ensuring you have a 5-meter gap between the connectors and the shell. Apply tape at each end to secure into place. Mix the resin for 3 to 5 minutes according to the manufacturer's instructions. Slowly pour into the resin shell and top up if necessary. Thank you from TE Connectivity.
Okay, so that's one method of doing a resin joint. Yeah, most of the time it will just be you've got that separating part. A lot of guys will still use heat shrink around the phase conductors just to ensure there's no accidental touching if those fail. Here's a similar system but slightly different.
Scott's Class standard premium LV resin joints represent a new generation of LV jointing products that are unique in the electrical contracting sector. These products are designed to make the installation process simpler and safer, saving time and money for the contractor, while maintaining the level of quality and reliability our customers have come to expect from 3M.
This is more for a
Scott's
steel
23
wire
self-care amalgamated is used to seal the clutch of the cable. The cable is then cut to length. If necessary, the joint shell is large enough to accommodate the crossing of phase cords. Station is then removed and connectors are installed. A number of our kits come complete with connectors for ease of selection. However, any connector can be used provided they do the requirements of the cable and fit dimensionally within our joint. Scott's 23 self-amalgamated tape is used to overtake the connectors. Ladders apply tightly around each connector, overlapping into the primary installation on each side of the connector position.
Use
The cable
calculated
is up to
tape
1
using
kV.
heat shrink.
3 half lap layers are applied. For unscrewed 3.3 kV, 6.6 kV cables, this is increased to 500 kV. To avoid awkward manipulation of arm wires while trying to fit worm drive clips over support pins, we have chosen to use constant fault screens as our preferred method. A quick and easy solution, requiring the minimum of fuss and no extra tooling. Scott's 23 self-amalgamated tape is used to overtake the constant fault screens, ensuring it is applied in the same direction as the constant screen. The cable shield is then braided to remove any contaminants to ensure the resin bonds to the cable jacket. Our mold body construction has a unique top seal and fixing clips, enabling a simpler installation process with no need for extra taping and a reduced chance of resin leakage. Foam seals at each end of the mold body can accommodate a range of cable sizes with a tight, reliable seal. The two foam sealing elements can be adapted to the required cable diameter by removing the pre-cut adapter wheels. To ensure the correct fit, position the incision on the foam seals in an upright position. This innovative feature means that sawing and taping the ends of the resin mold shell can be eliminated. Alongside the development of new joint mold body, we've also redeveloped our resin compounds to comply with EU environmental and user safety regulation changes, and all are REACH and RoHS compliant. Our innovative resin bag is designed to eliminate almost any chance of skin contact and reduce vapor inhalation from the resin itself. Furthermore, it gives the user superb control over the resin mixing and pouring process, avoiding unnecessary spills and wastage. Fully integrated resin delivery system is a new design for a quicker and safer installation. We are so confident of the safety of our resin delivery technology that gloves are no longer necessary. It's the reason why they are not found in our premium and standard low voltage kits. The Scott's Cast standard resin joints are ideal for general purpose street lighting and service cable jointing.
That's a couple of demos of how a resin joint is done for cable. Second one obviously being armor cable. The most important part with the resin joints is that you thoroughly mix the resin, otherwise it won't set at all. And I mean, preferably you don't have to do it. Yeah, sometimes you have to, especially when if you're doing a housing development, someone comes along and cuts all the cable coming up through the slab for your mains cables, and you have to pull it out underground and join a new piece on, which we had to do about 14 times on one job. Not to the same cable, but 14 different cables. Cool. So now let's look at 3008 1.2, electrical installations, selection of cables. Cool. So the purpose of AS-NZS 3008.1, it's an essential standard in the electrical industry that provides guidelines for current carrying capacity and installation conditions for cables. Its purpose is to help electricians select cables that are both safe and efficient under various operational environments. This document ensures that cable selection takes into account factors like temperature, installation method, and environmental conditions, reducing the risk of overheating and potential hazards. So it looks at the current carrying capacity of each type of cable, type and size commonly used in New Zealand, and the common environments that you'll find it in. So whether it's very direct in an enclosure, fully surrounded by insulation, partially surrounded by insulation, and all those kinds of things. So the scope of AS-NZS 3008.1 covers various technical parameters for cables, such as their insulation types, configurations, and installation methods. It covers common cables used in the industry at working voltages of up to and including 0.6 /1 kV at 50 hertz, and includes tables and guidance on calculating the appropriate cable size based on the current load and the physical environment. This ensures compliance with safety standards, particularly when cables are subject to environmental stresses like moisture, soil, and extreme temperatures. So it's how the standard we use to choose cable. When the cables are, the cable calculators that you're using are doing their thing, they're using calculations and tables from 3008.1 and various other things to do current carrying capacity and volt drop at the same time. But this is one of the ways to do it old school, because you can't always trust those cable apps. Sometimes they'll get it wrong, and sometimes you have to do one run in this size. You always choose the worst environment that is going to go through, the lowest value. Cool. So current capacity of cables. So one of the primary uses for this, AS-NZS 3008.1, is to determine the current carrying capacity of different types of cables. This capacity varies depending on the installation environment, e.g. cables in free air, buried in the ground, or enclosed in conduit. The document includes detailed tables that allows electricians to identify the maximum current a cable can carry without overheating. This ensures the cables can handle the required load safely, even in challenging conditions. But one thing to remember is that we protect the cable, not what's plugged into it. Okay, so if we've got a 2.5 cable, in certain conditions, we can only hook it up to a circuit breaker that will allow it to work up to a certain rating. So we can't. Same with 1 mil, depending on the situation. 1 mil is usually only rated up to 6 amps in standard configurations. But yeah, for example, if you're doing a switchboard upgrade and for some reason someone's already ripped the switchboard out, all you've got is a bunch of cables sticking up out of the switchboard, other than knowing, okay, it's a PowerPoint circuit, it's a hot water cylinder, things like that. You can look at the cable size and go, cool, this can only be put on a 6 amp breaker, 10 amp, 16, 20, 25, 32. So that's how you know how much it can handle. We do kind of go off some rough things, like you only ever put 6 mil on a 32, 4 mil is only good for up to 25, and 2.5 you stick it on a 16 or a 20. Those are kind of rough rules, and it's what we've learnt from 3008.1.2 that informs the tradesman kind of, oh yeah, I know this, I can put it on this. Even though your tradesman will pass it on to you, it's still good to know where that comes from. And you'll go into it a lot deeper when you go into year 2 and 3. Of course, the volt drop across cables. Another key component covered in 3008.1 is voltage drop. As electricity travels through cables, some energy is lost due to resistance, causing a drop in voltage along the cable length. Like we talked about, the volt drop across resistors in a series circuit. Basically, the cable is your series circuit, so there's going to be a volt drop. Provides guidance on acceptable voltage drop limits and offers tables to calculate voltage drop based on factors such as conductor material, load, and cable length. By following these guidelines, electricians can ensure that equipment receives adequate voltage and operates efficiently. Cool. Bit of a disclaimer. This lesson is in no way a comprehensive guide on current carrying capacity and volt drop. This comes later in your training. This is an introduction to the standard in relation to the studies you've been doing up to this point. It is another perspective of cable handling and selection from the angle of compliance and regulation. There are a lot of tables in the standard that will not be relevant to you as you work through your studies to become an electrician. The main tables we will look at will be current carrying capacities, tables 4 to 21, mainly table 10 and 13. Rating factors, tables 27.1 and 27.2. And you got your three-phase voltage drop, tables 40 to 51, but mainly table 42 and 45. Cool. So what's the... Cool. So what experience do you have with running a common socket outlet circuit in a house with or a small installation? What cable would you normally use? Too far? Yeah. Okay, how long do you think the cables from the main switchboard to the final socket are? Yeah, I know some of you guys have never done it. How long do you think the run is? $40 to $50? Cool. What are we looking at? We're looking at table 10 and 13. Cool. This is table 10. Cool. So yeah, cable type, 2-core sheath. Thermoplastic, maximum conductor temp 75 degrees, reference ambient temperature 30, and 15 in air and 15 C in ground. So here you've got your spaced, your unenclosed touching, exposed to sun, wiring enclosure in air. These are not the standard ones we would normally do. That comes down here. So you've got thermal insulation, partially surrounded by thermal insulation, partially surrounded by in a wiring enclosure, completely surrounded in a wiring enclosure. So this is more for your 2-core, so like your mains. But we'll look at 2-core, say 16 mil. So you'd normally have it running partially surrounded by thermal insulation. You wouldn't normally have it enclosed. So copper, we can have that up to 73 amps. But if it's partially surrounded by thermal insulation and in a wiring enclosure, that rating drops to 62 because it can't pass the heat through the air and then the thermal insulation. And then if we put it completely surrounded by thermal insulation, it dropped down to 46 amps. And then completely surrounded by thermal insulation and a wiring enclosure drops down to 39 amps. But then if we go to very direct, that 16 mil can handle 125 amps at 16 mil. And an underground wiring enclosure, solid or stranded, 95, and flexible, 94. So it's a very wide range of cable current carrying capacities that we have. But because when we run our cables, especially in the ceilings, they're normally partially surrounded by thermal insulation. It's not often we put them in wiring enclosures or they're completely surrounded, unless the builders hate us. So for most of its journey, it's partially surrounded, and so we can have it at 73 amps. But most of the time, your protection on your street is 63 amp or 60 amp fuses. So even partially, so when it's completely surrounded, we can't have that. So we have to make sure it's not completely surrounded by thermal insulation or use a different type of cable. And then if we look at exposed to sun or space, this would be for your overhead. You can have 97 for stranded, for exposed to sun, 68. So if it's exposed to sun, like outside, it can only carry 68 amps max. Then if we look at table, oh, this next one, 13. I want pictures. I like pictures. 12, 13. 3-core and 4-core thermoplastic. So this is your TPS. So yeah, 75 degrees max, 30 degrees C in air, 15 in ground. Cool. So we look again at the exposed to sun, like our overhead mains. Whoop, it's dropped to 58. So we're not supposed to have TPS or 2.5. It can only handle 19. Enclosed in a wiring enclosure in air, handle 23 amps. If we go down to partially surrounded by thermal insulation, 19. Or completely surrounded by thermal insulation, 13. Cool. Now we look at rating factors, table 27. Now to go ways down. Oh, gone too far. Table 27. This is what we call rating factors. So air and concrete slab ambient temperatures. So if we know the conductor temperature, so air and concrete slab ambient temperature. So for heated concrete slab, the ambient temperature shall be taken as the operating temperature of the slab. Normal usage of high temperature insulation cables, ambient air temperature greater than 30 degrees C, see table 17. So if we know what the conductor temperature is going to be, and this is the air and slab concrete ambient temperature. So we know the concrete is going to operate at 50 degrees, and the maximum conductor temperature is allowed to be 75. When we work out our cable carrying capacity, we have to times it by 0.72. This is because the current carrying capacity drops as the temperature increases that it's operating at, and the maximum temperature it's allowed to operate at. So, for example, if we know it's only going to be in 15-degree ground and the cable is allowed to operate at 75 degrees, we can actually increase the current carrying capacity because of these factors. That's point one. And then point two, you've got the rating. So this is your soil ambient temperature. So this is for air and concrete slab. And here's your soil ambient temperature. So 30 degrees, allowed to operate at 75 degrees. We have to derate it. 15 degrees, doesn't matter. It's just one. Anything below, we can increase. Anything above, we can decrease. And then let's have a look at voltage drop tables real quick. Just have a look at them. So you just need to know these exist at this point. You guys will cover them a lot more in year 2 and 3. So here we go, 42. So 3-phase volt drop. So this is the conductor size here. This is the conductor temperature. Cool. So example, 75 degrees, 2.5. The maximum volt drop, 15.6 at a 0.8 power factor, which you don't need to know what that is right now. 15.6. So this is the allowable volt drop, or the volt drop. Cool. And then if we look at table 45, and you guys just need to know these things exist. Yeah, 3-phase volt drop, multi-core cables with circular aluminium conductors. So table 42 was multi-core copper, and then 45 is multi-core circular aluminium conductors. So you just need to know these things exist at this point. Cool. Cool. So current carrying capacities are based heavily on the factors we've talked about just now. There's a variance to ambient temperature. We need to uprate or downrate the cables using the different tables. Once we have the right table, we scale it down within the table to the right columns. Firstly, we pick the right environmental condition. Then if is it copper or is it aluminium? If it's copper, is it solid, stranded, or flexible? So for example, condition of the cable will be spaced and a stranded copper conductor. If we choose 2.5 for the socket outlet, what is the maximum current carrying capacity? So here's section of the table for reference. So what's the, for spaced, what's the maximum current carrying capacity? A 2.5. So it's solid, it's stranded, and it's spaced away from anything. What is the current carrying capacity? Cool. Cool. Answer 26 amps. Yeah. Yeah. All you have to do is come to the table, the conductor size here, 2.5. We know it's spaced. We know it's solid and stranded. So we just cross-reference the two, 26. But if it was flexible, we'd have to drop it down to 25. Cool. And as simple as that using the tables. Cool. Cool. However, this is not usually not the case in New Zealand. In fact, ASNZ 3000 states that if not otherwise specified, we must assume that any cables run in a domestic residential installation is partially surrounded with thermal insulation. Cool. So what's the maximum current now? Yeah, it's 19 amps. Cool. Because if we come across here, conductor size, partially surrounded by thermal insulation, unenclosed. That's another key word. So this is a wiring enclosure. This is unenclosed. And we come down copper, 25, 19. And of course, aluminium, not allowed to use any of these sizes for anything enclosed in insulation. For me personally, I've never had to worry too much about insulation because most of my jobs have been commercial and big buildings where you don't use a lot of it. Cool. So those are the two side by side. You can see the difference. As soon as we are partially surrounded by thermal insulation, we lose 7 amps worth of current carrying capacity, which is why most of the time in domestic you'll see 2.5 cable on a 16 amp breaker rather than a 20. Cool. What about if we bury the cable directly underground? What happens then? Cool. So we look at this table. We look at very direct over here. We come down to 2.5 and it jumps up to 31 amps. Very direct. Now, the thing is, TPS, we're not allowed to bury it direct. It's not rated for it. No, guys, you'll get the wrong one. So instead of being partially surrounded here, it's very direct. If we come down to the copper, 2.5 there, it's 31 amps. Yeah, as soon as we, cool. So why does this happen? Why can we now, why is it such a high current carrying capacity now that it's underground? Yep, it gets colder, so it drops down from 30 to 20 to 15. So it's 30 in air, 25 in 35 in air, 15 in. Anyway, it drops down to lower temp, so the cable can then carry slightly more current. The reason for this is the cable's ability to dissipate more heat and not burn out as it can now dissipate into the air rather than trying to dissipate through the thermal insulation. Can dissipate into the ground, which is colder, rather than trying to dissipate through the insulation, which doesn't want heat to transfer. Okay, so that's basically it for tonight. I am going to go back, stop the recording now. From now, what I want you guys to do is you guys can access this standard